Hello everybody, so welcome to the session on radius of curvature. Here we will be discussing what is the radius of curvature, what is the intrinsic form, and how to calculate it in general. So given this curve here, if P is a point on the curve, Q is a point in the neighborhood of P, and N is the point of intersection of the normals at P and Q, and let N tend to C as Q tends to P. So C is called the center of curvature at P. And Cp is the radius of curvature. It is denoted by rho, and rho is ds by d psi, where this is as distance between A and P, where A is any point, and the angle which this P makes with the x-axis is your psi. So intrinsic formula for radius of the curvature is ds by d psi, and curvature of the curve is the reciprocal of this d psi by ds. So curvature is 1 by radius of curvature. So let's go to a few problems. Find the radius for the curve whose intrinsic equation is s equal to a log tan pi by 4 plus psi by 2. So rho, the radius of curvature, is ds by d psi. That will be a log, derivative of log x is 1 by x. So 1 by tan pi by 4 plus psi by 2 d psi of tan pi by 4 plus psi by 2, which is secant squared pi by 4 plus psi by 2 into derivative with respect to psi of pi by 4 plus psi by 2, which is half. So when you simplify it, tan is sine by cos, secant squared is 1 by cos. So it becomes a by 2 sine pi by 4 plus psi by 2 cos pi by 4 plus psi by 2. Now 2 sine theta cos theta is sine 2 theta. So this becomes a by sine 2 into pi by 4 plus psi by 2. That is a sine pi by 2 plus psi, which is a by cos psi, that is a sec psi. So this is the radius of curvature for this curve. Now, what about the Cartesian formula for the radius of curvature? That is given by rho equal to 1 plus y1 squared raised to 3 by 2, the whole raised to 3 by 2 by y2, where you know that y1 and y2 are the first and second order derivatives with respect to x. Interchanging x and y, we get 1 plus dx by dy the whole squared raised to 3 by 2 by d2x by dy squared, and we use this formula when the tangent is perpendicular to the x-axis. That means when dy by dx is infinite. So coming to question 2, find the radius of curvature of the curve x cubed plus y cubed equal to 3axy at the point 3a by 2, 3a by 2. So we have x cubed plus y cubed equal to 3axy, differentiate with respect to x. So 3x squared plus 3y squared dy by dx equal to 3a. Apply the product rule here. So you get x dy by dx plus y ddx of x is 1. So open the bracket, you get, you can cancel out 3, and then you get x squared plus y squared dy by dx is ay plus ax dy by dx. Take the terms in dy by dx together and the other terms to the other side. So y squared minus ax dy by dx is ay minus x squared, or dy by dx becomes ay minus x squared by y squared minus ax. Now you need to find the radius of curvature at the point 3a by 2, 3a by 2. So first calculate dy by dx at the point 3a by 2, 3a by 2. Substituting y as 3a by 2, x as 3a by 2, and simplifying, you get it as minus 1. Now to find the radius of curvature, we need to find the second order derivative. So differentiate this equation 1 with respect to x again. So you get 2x plus 2y, apply product rule here, 2y dy by dx the whole squared plus dy y squared d2y by dx squared. Again apply product rule here. Now here it is just a dy by dx. Here for x dy by dx I need to apply the product rule. So I get a dy by dx plus a x d2y by dx squared. So take the terms in d2y by dx squared to one side. So you get y squared minus ax d2y by dx squared plus 2y dy by dx the whole squared. Then you have plus 2a, and when you take it to the left you get minus 2a dy by dx plus 2x equal to 0. Again substitute at the point 3a by 2, 3a by 2, substitute for x and y, and simplifying you will get d2y by dx squared is minus 32a by 3. So this is your radius of curvature, rho. Now, we have this formula 1 plus dy by dx the whole squared raised to 3 by 2 by d2y by dx squared is your radius of curvature. So substitute what you have got for d2y by dx squared and dy by dx in this equation. Dy by dx is minus 1, d2y by dx squared is minus 32a by 3. So simplifying you get minus 3a by 2 raised to 7 by 2. 5 minus 3 by 2 is 7 by 2. So this is your radius of curvature for this curve. Quite a bit of calculations, isn't it? Okay, we'll do one more question using the parametric form. Find the radius of curvature for the cycloid x equal to a into t plus sine t, y equal to a into 1 minus cos t. So x equal to at plus a sine t dx by dt will be a plus a cos t. Y is a minus a cos t, so dy by dt will be a sin t. Derivative of cos t is minus sin t. So as you have learned for parametric form, dy by dx is dy by dt by dx by dt. So you get a sin t by a into 1 plus cos t. Now cos 2t is 2 cos squared t minus 1. So 1 plus cos t becomes 2 cos squared t by 2. And sin t you can write as 2 sin t by 2 cos t by 2. So 2 and cos t by 2 gets cancelled. You get sin t by 2 by cos t by 2, which is tan t by 2. This is dy by dx. Again d2y by dx squared will be d dx of dy by dx. Applying the chain rule, it will be d dx of tan t by 2, that is half secant squared t by 2 into derivative of t by 2, dt by dx. That is half secant squared t by 2. Now dx by dt is a into 1 plus cos t. So dt by dx will be a 1 by a into 1 plus cos t. The reciprocal of that. And you just saw that 1 plus cos t is 2 cos squared t by 2. So d2y by dx squared, when you simplify, you get 1 by 4a secant raised to 4t by 2, taking this cos squared on top. And now you substitute in the formula. Rho is 1 plus dy by dx the whole squared raised to 3 by 2 by d2y by dx squared. That is 1 plus dy by dx is tan squared t by tan t by 2. So it becomes tan squared t by 2 the whole raised to 3 by 2 by 1 by 4a secant raised to 4t by 2. Now 1 plus tan squared t by 2 is secant squared t by 2 raised to 3 by 2. So it becomes secant cube t by 2 by sec raised to 4t by 2. The 4a I can take on top. So this becomes 4a, it becomes 4a by sec t by 2, which is 4a cos t by 2. So this is your radius of curvature in this case. So we have learned what is the radius of curvature, how to calculate the radius of curvature for the Cartesian and the intrinsic form. Thank you.